And okay, now what about P0 at some t plus delta t? So how much different it would be compared with P0t? And the answer is that, now notice for P0, there's nothing coming in. So you only have stuff going out. So P0, and here you have 1 minus lambda delta t. So from P0t, you're subtracting P0t multiplied by lambda delta t. So the stuff going out is proportional to lambda, and it is also proportional to the duration. So longer duration, more stuff goes out. And we can write this as, now this is the traditional stuff from your calculus. So if you still remember your calculus class, you probably remember this. Okay, anyone remembers this from your calculus, but probably took it a while ago. So, and basically from calculus you will remember that if delta t approaches 0, then you can write this as this. And solving that is not too hard. Let's get the solution here. Or why don't we come here for the solution. Let me see. Or maybe I guess I'll work here, solution. Okay, so here we have a differential equation, and let us solve this differential equation. And what we need to do is integrate this. So since you all know how to solve differential equations, so you will probably you will follow this. Basically, this is how people generally do it. Okay, we write the equation in this form. We integrate both sides. So when we integrate both sides, the integral of this is going to give us natural log of P0t, and that here we are going to have minus lambda multiplied by t. We have integrated it. And there is a constant of integration, which we are going to figure out soon. And now we can write this as, I rewrite this as P0t equal to some C2 e raised to minus lambda t. And maybe I can call this C1. There's a connection between C1 and C2, but we don't care really, because we are going to figure out what C2 is going to be. Now if we assume that initial condition is this, since P0 0 is equal to 1, let us assume that at time t equal to 0, the count was 0. That is in fact the assumption in the definition of the Poisson processes. So P00 is 1, and so at time t equal to 0, we want this to be 1, and that means, that implies that C2 should be equal to 1. And hence we get the answer P0 t is equal to e raised to minus lambda t. Now this is a rather famous equation. How many of you have come across something like this? So for example, when people talk about radioactive decay and a certain decay rate, in a number of situations where somehow the process is leaving some state at a certain rate, then you have this as the governing equation. Remember it, you are going to remember it. And now let us come, okay, so we have solved it only for P0. Now since we have P0, we can solve it for P1. So this is the equation, general equation we want to solve. So we can solve it for P1, then we can solve it for P2, and so on. And we are going to get the solving recursively. We get probability of being in some state, let's call it n, is given by, now you can verify that this is indeed correct fairly easily, but just to save time I'm going to skip the calculation, but you can easily do that calculation. And of course, as we know, this is your Poisson distribution. Any questions or comments so far? So basically, probability that you are in state n at some time t is given by this. In other words, probability that you have had n arrivals in time t is given by this. Now there is other part of this particular calculation. Let us talk about time between two arrivals. Now, so you have one thing arrives, next thing arrives, and of course they don't arrive deterministically, they arrive randomly. So the next arrival could be immediately afterwards, or it could take a while, but it is governed by some distribution. And so here we want to show that the time to next arrival, objective is that time to arrival, time to next arrival is exponentially distributed. So this is what we want to show. And so let us see this. And since it's not too long, let us consider the cumulative distribution function. Okay, you remember that the cumulative distribution function. So time between two arrivals, and let us call it t, uppercase T. So let us calculate the cumulative distribution function for uppercase T. So f of t is given by probability that time to next arrival is somewhere between 0 and t. This is the definition of distribution function. So distribution function is the cumulative between 0 to something. So it's cumulative between here and here, and it's a random variable. And that we have calculated as equal to 1 minus probability of no arrival in t, and that is equal to 1 minus e raised to minus lambda t. Now the density function, as you know, is the derivative of the distribution function, right? So if you want to get the density function, all you need to do is to take the derivative of this and you get the density function. So differentiating both sides, we get the derivative of this which is equal to the density function of this. Now sometimes I will drop this t because sometimes it will be clear which random variable we are talking about, and that will turn out to be lambda multiplied by e raised to minus lambda t. And this, as you see, is your exponential distribution. So this is this was an overview of probabilistic methods. So you have probably seen many of the things before. Even if you haven't, we have kind of looked at all the basic ideas that we are going to be using, even though in some cases I have skipped some of the mathematical details. And this is basically our toolbox that we are going to need in order to evaluate reliability. So when we talk about fault tolerance or high reliability, we want to be able to evaluate reliability. And next we are going to be looking at how to evaluate reliability. And let me briefly mention how we are planning to proceed. I'm going to give you some measures of reliability. There are actually several ways of measuring reliability. And then we are going to look at some basic cases, simple cases. And as we will see, the cases when the failures are permanent are somewhat different from the cases when failures are temporary. So we will look at permanent failures and temporary failures. And we then will look at, we are going to look at classical reliability theory. So there's a classical reliability theory, and there is a combinatorial block. So people have thought about that, okay, if you want to make something more reliable, and I have these different components, I put the components together, and some of the components are redundant, then what is the reliability that I can achieve if I connect them in a certain way? And so we are going to look at how to calculate reliability of systems which consist of blocks which have their own reliability attributes. And then we are going to look at some more at redundancy. So at the beginning, when we will look at classical reliability theory, we will look at some idealistic situations, and then we will look at some real situations. You will see if you add some redundancy, then what are the different schemes you can use and what kind of reliability you can achieve. So we will do that next time. So look for that homework assignment, and that is going to be due on Wednesday next week.